Hello everyone, my name is Gabriel Vieira. Today I'll be presenting our paper titled Gaze Estimation via Self-Attention Augmented Convolutions. This work has been developed alongside Professor Luciano Oliveira at the iVision Research Lab at Universidade Federal da Bahia. Our main goal was to explore if the recent trend of attention mechanisms in deep learning could be successfully applied to appearance-based gaze estimation. First, I'll do a brief introduction of the gaze estimation problem and present the intuition behind our proposed solution. After that, we'll go over some relevant works in the current literature that both inspired our research and served as comparison baselines for our validation experiments. Then I'll lay out the specifics of our proposal, going into further detail on design decisions and relate that to the gaze estimation problem. Finally, I'll show some experiments we made to validate our hypothesis and how our model performed against other comparable methods in the literature, before going into the conclusion. So let's get into it. Conceptually, gaze estimation is the task of determining the direction of a subject's gaze, or in other words, their visual attention, as illustrated by the red arrows in the presentation. In the context of our work, this would be achieved by obtaining a gaze vector g hat, whose origin is the middle point between the eyes, and whose direction is described by the pitch and yaw angle components. As for the estimation task itself, our work focuses on the appearance-based gaze estimation. Simply put, the objective is to extract the gaze vector information directly from images of the subject's eyes and/or face. This is generally done by training some sort of learning algorithm to act as a mapping function between the images and the gaze information. Other methods, like model-based approaches, for example, usually rely on strictly controlled environments and precise geometrical modeling of the visual system. While these can produce very accurate results under the right conditions, appearance-based approaches have gained a lot of popularity over them since they are more robust to real-world conditions, and recently the use of CNNs as mapping functions has produced comparable or even better results while having less hardware and environmental restrictions. With that out of the way, I'd like to take some time to go over some works that tackle the same problem and that have served as inspirations for our research. We have selected a subset of those that had the biggest impact in our final proposal, but they are definitely not the only ones. For more details and other relevant papers in the field, please refer to the full paper. The MPI gaze framework was one of the first to successfully use CNNs as the mapping function of an appearance-based gaze estimation model, and it uses a very simple, straightforward approach. A convolutional neural network is trained on a dataset, also published by the same authors, of eye images annotated for pitch and yaw gaze angles. The network itself is a simple CNN that outputs a feature vector of size 500. The head pose angles, represented here in the image by the letter H, are then concatenated to the feature vector, and the resulting vector is passed through a regression layer to obtain the final values. It's important to note here that head pose is an important factor to appearance-based gaze estimation, since the final direction we look at might vary heavily as we move our heads, even if we don't move our eyes. This fact will come up again further on in our presentation, so just keep that in mind. Another work I'd like to mention is the eye tracker. The system was specifically designed for 2D gaze estimation on mobile phones. That is to say, we no longer want to infer a 3D gaze vector, but specific 2D coordinates on a plane. In this case, the plane is represented by the phone screen. This doesn't have a big impact on the network design side of things, being more related to the kind of data that you use to train the model. The network structure itself is much more complex than what we saw previously. Now we have a multi-input structure with not only the eyes being forwarded through the CNN, but the face is also being used as an input to a completely separate backbone. Additionally, the authors chose to include a face grid input, which indicates the general area where the face is located on the input, which is particularly helpful for the 2D projection aspect of this system. All of the outputs are mixed by concatenations and fully connected layers before finally producing the final X and Y coordinates. The last reference I'll be showing here is the spatial weight CNN, which was published by the same team behind the MPI gaze architecture and dataset. The authors published an extended version of the MPI gaze dataset that included full-face images from subjects and presented a more complex CNN structure to deal with that. Now, obviously, the eyes have been replaced by faces as the inputs, but I'd like to point out they have also removed the explicit concatenation of head pose angles to the feature vector, with the hope that that information would be implicitly inferred from facial images themselves. The other important point here is this middle section labeled spatial weights. The authors came up with the sequence of 1x1 convolutional layers followed by activation layers that had the sole purpose of learning which regions of the input images were the most relevant to the prediction task. The objective here was to help the CNN focus on important regions like the eyes and the nose, while being less susceptible to noise from features from unimportant regions like the forehead and the cheeks. As I said previously, these were only a few of the important works in the field that helped inspire this paper, and in this next section, hopefully, you'll be able to see how each of them impacted our final proposal. We'll first give some context on why and how we chose to use self-attention in our model, and then we'll discuss how that fits into our proposal for the gaze estimation task. Our work focuses on improving the accuracy of the mapping function of the appearance-based model, which in our context is a convolutional neural network. For that, we imagined that the recently developed attention mechanisms would be a good fit given the task. Why? Well, one of the main advantages in using self-attention mechanisms is their ability to model long-range context into features. On image applications, this translates to the model being able to learn correlations between relevant features in different regions of an image. This has already been demonstrated to yield good results for classical applications such as image classification, for example. Now, with regards to gaze estimation, the intuition is simple. Gaze itself is an inherently spatial phenomenon. For example, if we're looking at a picture of someone's face, the eyes are the obvious indicators of where that person is looking at, but like we already saw, other regions like the nose, the chin, and the ears even are also strong predictors for the gaze direction. Being able to learn to take them all into account, especially with how they impact one another, should produce better results than just taking hints from them separately. As a way of incorporating attention into the mapping function of our method, we use attention-augmented convolutional layers. One pass through one of these layers implies one pass through a regular convolutional layer and one pass through multiple attention heads that ultimately produced a mixed attention-augmented feature map. Now, we chose these layers since they can be used as drop-in replacements for regular convolutional layers, making it easier to compare evaluations between attention-augmented and regular networks, and by consequence to isolate the effect of attention augmentation in the gaze estimation task. Now, more details can be found in our paper and of course on the original publication. As a baseline, we used a regular ResNet 18 architecture with one input stem, 4 convolutional blocks, and one global average pooling layer before the output. From there, we keep the input stem as a regular convolution and keep the same gap layer on the output while replacing every convolutional in the core blocks with attention-augmented ones. Now, training these layers is a very resource-heavy process, so due to hardware constraints, we also removed the last convolutional block entirely. This leaves us with 14 convolutional layers, which is why we will refer to this architecture as Aries 14 for the remainder of the presentation. Building upon the Aries 14 architecture, we now present our final gaze estimation framework, a multi-input dual-branch architecture dubbed Aries Gaze. As inputs, we used images from the subject's face and the subject's eyes. These are then passed through 2 separate parallel Aries 14 branches, and the extracted features are then joined by concatenation and mixed by sequential fully connected layers to produce the final output, which are the pitch and yaw gaze angles. Now we can move on to the experimental portion of the presentation. Here I'll briefly also discuss what datasets and premises we adopted to evaluate our proposal. Now, due to time limitations, not all experiments we performed will be covered here. We'll go through some of the more interesting results and see how our model performed against other comparable approaches in the current state of the art. but if you wish to see the full extent of the experiments and result interpretation, please refer to the paper. We'll evaluate our model on the MPI phase gaze and eye-diap datasets. They are two of the most widely used datasets for in-the-wild appearance-based gaze estimation evaluation. We chose them not only because they're used by the majority of the related works, making comparisons easier and fairer, but another important factor is that they complement each other pretty well. For example, the eye-diap dataset has a great deal more variation on head pose, but due to being collected in heavily controlled lab environments, it lacks the illumination conditions and overall quality variety found on the MPI phase gaze dataset, as you can see on the samples. We'll split the experiments in two main sections. First, we'll focus on the overall impact of attention on each part of the framework, as we try to isolate what works and what doesn't when it comes to gaze estimation. In the second, we'll try to see if attention is at all helpful in any particular way with classically challenging aspects of the in-the-wild gaze estimation task. First, we evaluate the effect of attention in each section of the Appearancebased framework. We train 4 different versions for each dataset, alternating the branches between baseline and attention-augmented versions. By comparing the average angular error in each scenario, we can see that the face branch of the framework benefited more from the use of self-attention than the eye branch on average. This aligns with our initial hypothesis, since on the facial input there is relevant information in multiple regions of the image, while on the eye input the gaze-relevant information is condensed to a single region, the pupil. It's also worth noting that the version with attention only on the eyes actually performs slightly worse on the MPI phase gaze dataset. On both datasets, the use of self-attention on both branches yielded the best results overall. Moving on to the external factors now, we'll also evaluate the effect of self-attention when dealing with extreme pose angles, as demonstrated by the images. They are samples from the eye-diap dataset, which we're going to use for this experiment. We group evaluation samples in increments of 0.2 radians for the pitch and yaw angles, and evaluate the average angular error for each segment. Blue represents segments where we had a reduction of the error, and red represents segments where there was an increase of the error. Overall, the magnitude of improvements was larger than that of the errors, with the notable mention on extreme pitch angles, which had the greatest improvement overall. When looking at this plot, it's not unreasonable to consider that the gains we had on the eye-diap dataset were mostly due to the significant increase in accuracy we had on the more extreme pitch samples. Earlier we mentioned that MPI phase gaze had a significantly greater variation of illumination conditions than eye-diap. We decided to evaluate if attention had any positive impact on this factor by conducting a similar experiment here. We grouped the evaluation samples in tranches by their average grayscale light levels and measured the average error in each tranche. What we found was that there was no significant impact of attention on the performance with regards to illumination. This further reinforces the hypothesis that head pose angle robustness was responsible for the greater magnitude of gains on the eye-diap dataset. Finally, we compare our approach with multiple methods from the current state of the art. We were able to reach the best results with the Appearancebased gaze framework on one dataset, MPI phase gaze, while reaching second place by a slight margin on the other one, eye-diap. In conclusion, we were able to ascertain that the use of self-attention was indeed beneficial to the appearance-based gaze estimation task. Given the shallowness of the attention-augmented backbone use, ARIS 14, we reinforce our hypothesis that self-attention is a very promising avenue to explore with regards to gaze estimation. We also show that facial images have more to gain from the use of self-attention than eye images, which leads us to believe that a framework with specialized architectures for each type of input might perform as well or even better while having less training overhead. Additionally, using other modalities of features like facial landmarks, for example, might improve the results or even open the way for other interesting tasks like jointly predicting head pose and gaze angles by leveraging the spatially aware facial features. Thank you, I hope you enjoyed the presentation, and please don't hesitate to reach out if you have any questions or comments.